As a child, I've always had a positive experience with going to the dentist. I made sure to have no cavities by flossing and brushing my teeth for exactly 3 minutes every night. My passion for maintaining my oral hygiene has inspired me to become a pediatric dentist in the future. During the summer, I was given the opportunity to shadow my pediatric dentist, Dr. Brenda Ho, and work as a dental assistant. My job consisted of mostly cleaning the dental chairs and setting up dental trays, but I would occasionally help sterilize the dental tools. The straightforward yet intriguing process caught my interest as it reminded me of baking. As I was deciding on my topic for the final project, I had a hard time figuring out how I could relate calculus to my previous job. However, I realized that I could calculate the rate at which microorganisms are being reduced during sterilization using the autoclave machine. Hello, my name is Zoe Fang, and my final project will explain how calculus is involved in dental sterilization. So what is sterilization? Sterilization is a treatment method to deactivate viable microorganisms from objects and products. Basically, it's just preventing cross-contamination from occurring through using a thorough cleaning process. And we can categorize sterilization into 3 categories: thermal, chemical, and radiation. But for the sake of this project, we will be just talking about thermal sterilization, more specifically, moist heat. So how does dental sterilization work? We use a machine called the autoclave, and it basically utilizes steam to reduce microorganisms. And it does this by reaching a specific temperature and maintaining that desired temperature until it provides a lethal effect of microorganisms. So how does an autoclave actually work? So there's 3 phases, and it's shown here in this graph. The first phase is the purge phase, and it's when the temperature and pressure of the autoclave rises to the desired temperature. The second phase is the exposure phase, and this is where sterilization occurs. It does this by maintaining the desired temperature so that it provides a lethal effect. And after the sterilization has been complete, then it goes to the exhaust phase, which it returns to the ambient temperature. So how is calculus involved in this process? Well, after doing so much research, I found a formula which gives us the cumulative lethal effect of heat at the given temperature and time. So we can use this formula to find the lethal effect of heat on bacteria in dental sterilization. And because we are dealing with moist heat, the most commonly accepted Z value for most bacterial spores is around 10 degrees Celsius. So throughout this entire presentation, our Z value is just going to be 10 degrees Celsius just for simplicity because we are dealing with moist heat. So let's understand our values a little bit more. F initial is just the lethality rate. Lowercase t is the sterilization in time in minutes. T naught is the reference time. It's usually set at 3 minutes. Capital T is the actual temperature of the sterilization process in degrees. And lastly, our Z value, which represents the temperature change required to achieve a 10-fold change in the microbial death rate. And like I said before, because the Z value is very specific to the microorganism, the Z value can vary, but just for the sake of simplicity, our Z value is just going to be 10 degrees Celsius because we are dealing with moist heat. So how much time does it take for the bacteria to be reduced? We can use integration to answer this question. By using integration, we can obtain an accumulation of bacteria being killed. Like I said before, Z value is 10 degrees Celsius, and after doing some research, I found out that typically for an autoclave, if an autoclave has a desired temperature of 180 degrees Celsius, then the time it takes to complete the full sterilization process is about 30 minutes. So capital T is going to be 180 degrees, and lowercase t is going to be 30 minutes. And because we are trying to find the accumulation of bacteria during the entire time of the sterilization process, we're going to be using a definite integral from 0 to t prime. And just for notation's sake, we're going to change f naught to L of t prime just to make it less confusing. So let's go through our step-by-step solution. So first, you want to evaluate the integral by putting in our limit in our integrand. Next, we want to factor out any constant that has no dependency on t. And in our formula, 10 to the power of all these values has no dependency on lowercase t, so therefore we will be factoring out. And then once we have our integral, we're going to evaluate it and then calculate the antiderivative. So we have our integral right here, and we found the antiderivative right here. After we found the antiderivative, we can then apply the fundamental theorem of calculus. And if you fully write it out, this is what it should look like. But just to simplify it, this is what our formula is going to be. So let's do an example problem. How much bacteria is being reduced in the autoclave for 30 minutes? So with our formula that we were given from the last slide, we can just plug in our values. So capital T is 180 degrees, Z is just 10, our lowercase t is going to be 30 minutes, and then t initial or t naught is just going to be 3. So after you put in all your values and you plug it into a calculator, this is what your number should be. And as you can see, it's a very large number, which is good because the longer the tools are in the autoclave, that means that more microbes are being reduced. So you want a large number. So this is our answer. Here are my notes. So how can we determine on average the number of bacteria being killed? So we can use the average volume theorem. The average volume theorem is just an application of integrals, but it basically will help us determine the average number of bacteria being killed. And we will be using the same values as we did with the integration problem, except the only difference is that with the average volume theorem and its formula, we're going to use 0 to t prime as our a and b values respectively. So here's our step-by-step solution. So first we have the mean value theorem formula, and then we're going to replace f of x with L of t prime. And then once we have that, we can just plug in our formula. Our step 2 is we could take our previous integral, like we answered previously. And we can actually simplify this a little bit more by dividing our integral by our b value, which is just t prime. So once we simplify everything, then we get this as our formula. So let's do this example problem. What is the average number of bacteria being killed in 30 minutes when capital T is 180 degrees Celsius and the Z value is 10 degrees Celsius? So with our formula that we figured out in the last slide, we can just plug in our values as well. So like I said before, capital T is 180 degrees, our Z value is 10, our lowercase t is going to be 30, and then our T initial is just 3. And then once you plug it into a calculator, we found out this is our answer. So this number is going to be our average number of bacteria killed in 30 minutes. Here are my notes. So lastly, how can we find the change of rate with respect to time? We can do this by using the partial derivative to find the change of rate with respect to time. And what we're doing is basically just finding the rate of change. It sounds a little confusing, but once we work it out, it will make more sense. So here's our step-by-step solution. We're going to take the partial derivative with respect to t. Then we're going to factor out any constant that has no dependency on t. And then once we do that, we have our partial derivative, and we're just going to find the derivative of that. And we're just going to, any variable is going to be 1, and any constant is going to be 0. So this is our partial derivative. And once we simplify everything, this is our formula. And let's work out this last example problem. What is the change of rate of the formula with respect to t? Capital T is 180 degrees Celsius, and the Z value is 10 degrees Celsius. So we have our formula from the last slide, and all we have to do is just plug in our values. And once you do that and you calculate it on a calculator, this is what your answer should be. So the change of rate of the formula is going to be this number. Here are my notes. So we use integration to find the accumulation of bacteria, and then we also use the average volume theorem to find the average number of bacteria being killed during the sterilization. And lastly, we use a partial derivative to find the change of rate with respect to time. Here are my references that I used throughout my presentation. And that is it. Thank you so much for listening.